你所畅想的未来，是我想要创造的现在。化图景为现实，一路荆棘而来，哪一刻是永生难忘
？I'm Professor Dennis. I'm an inventor of a technology called non-invasive prenatal testing, NIPT. So this is a part of our laboratory. Actually, when I walk along this laboratory, it really brings back old memories, because when I come back 25 years ago, only about 6 feet of space. So we're very fortunate to be given all these spaces now. You see many tweezers. These are basically the treasure of our laboratory. They are very valuable samples because they're donated by the women and patients whom are looked after by clinicians, and we thank them for the trust in our laboratory. Hello, friends of Alibaba DAMO Academy. Welcome to DAMO X Time. So remember that in Oxford, I have to study different subjects, and one of those subjects was obstetrics. So I learned about how when a woman is pregnant, she would like to know about the genetic health of the baby. But at that time, the most accurate method is invasive. It's a technique called amniocentesis, in which a big needle is inserted into uterus, and then some fluid is taken from the uterus. But every time you do this, there's a risk that we may harm or even kill the baby. And so as a young male student, I was wondering, why did doctors do such dangerous things? Is it possible to develop something safer? So I thought, would it be possible to develop a blood test which we could do from the arm of the pregnant mother and be able to tell about the health of the baby? So I was thinking about whether during pregnancy, a baby might release its cells into the bloodstream of the mother. And so at that time, I was in Oxford, and I remember actually once I went to a lecture by Professor John Bell. And then during the lecture, Professor Bell taught us about a then new technique of polymerase chain reaction, or PCR for short. So basically, PCR is a technique which allows us to amplify the signal of DNA. And I remember vividly that he told us that he thought that this technique is going to change the world. And I believe him. So I remember that after the lecture, I actually went to see him and I asked him to teach me the technique, which he very graciously did. And so I learned about how to use PCR. So I was thinking, is it possible to actually use PCR to detect the fetal cells which may have entered into the mother's blood? And so I managed to persuade a couple of professors to let me do this in their laboratories. So remember at that time that I have to have a way to demonstrate that whatever cells that I was detecting was from baby, that at that time I should be able to see male fetal cells in the mother's blood. And then I remember that I work as a junior doctor in the hospital, but constantly thinking about this field, because I thought that I've started it, and so I have a responsibility to finish it. So I decided after 1 year to actually stop training as a doctor, but actually to go back to Oxford and work full-time as a PhD student. But then when I started working on this project full-time, then I realized it wasn't as simple as I thought, because the number of fetal cells we see in the mother's blood was actually very, very low. And so after 3.5 years of work, I still couldn't actually get a system to work robustly. And so then after that, I remember my scholarship finished, and so I have to go back into clinical practice and not solving a problem. And then I worked as a doctor for a few more years until 1997, when I actually decided to come back and join the Chinese University of Hong Kong. And then I remember that coming back, I would need to pursue a new research direction. So at that time, I remember actually seeing a couple of papers in a journal called Nature Medicine, which talk about in cancer patients, we have cell-free cancer DNA in the blood of those patients. And then I thought, well, a baby living inside mother is actually a little bit similar to a cancer growing in a patient. So maybe we can also have the fetal DNA in the cell-free part of the mother's blood. So I've decided to actually go and test it. But interesting, we actually managed to see that there's indeed cell-free fetal DNA in maternal blood. And it was the first time that we have shown this. And then, after that, we actually spent a lot of time elucidating the biology of this phenomenon. For example, we asked, what is the concentration of fetal DNA in the mother's blood? What time, what gestational age can we see it? And we showed that we can see it very early on, in 5 to 7 weeks of pregnancy. And what happens after delivery of the baby? And we showed that actually within 2 hours after the baby is born, the DNA is gone. So that is very good news, because it means that fetal DNA will not persist from one pregnancy into another. And then we thought, well, how can we use this for some prenatal testing purposes? So we start slow. We start a simple one. First, we actually showed that you can use it to determine the sex of the baby, which is useful because some genetic disease are mainly affecting boys, like hemophilia or Duchenne muscular dystrophy. And then we also show that we can detect the fetal blood group type of the baby, because sometimes if the mother and baby have different blood group types, then the mother could attack the baby immunologically. And after achievement of those, then we thought, well, we can be more ambitious and actually try to address the number one reason why pregnant women go for prenatal testing. And that is they're worried the baby may be suffering from Down syndrome or other chromosome aberrations. But interesting, that journey actually took me 10 years. We started that in 1997, and it took us 10 years to do it. And the reason is because we have to try to actually look at the problem from different angle and try to solve it. And one of the fundamental difficulties is this: in the mother's blood, most of the DNA molecules are actually from the mother, and the fetal DNA is only a minor portion. So in other words, whatever signal we're detecting is mainly from the mother. And the second problem is that conventionally, if you try to prove that a baby has Down syndrome, you have to take a cell from a baby, and you see a cell, and you count how many chromosomes we have inside the cell. But the problem in my phenomenon is that there's no cell, right? All the DNA is swimming outside cell. So how can you count how many chromosomes is inside cell? So in the end, we actually work out that we can actually detect that by measuring the ratios of different chromosomes. And so basically over that 10 years, I tried different methods, different technology. We try to detect the gene expression pattern from baby. We try to look at biochemical modification called DNA methylation. And eventually, we actually find that one good way to do that is to count the fetal DNA molecules, molecule by molecule. So first we use a digital PCR or single molecule PCR, and then we use sequencing. So another reason why we think that we eventually succeed is that we're able to use at any particular time the most advanced technology that is available at that point. And then also another very good thing that we have is that I work in a hospital. So we're able to establish very good collaborations with our clinical colleagues. So over that period, we're able to actually do the first large-scale trial, clinical trial of this technology, and show that it has an accuracy of over 99%. In this journey of discovery, one thing which I've found, which is very interesting, is that we frequently is able to actually obtain what we do in daily life and try to get inspiration of that. Now, for example, I remember when I was first working at fetal DNA in maternal plasma. So at that time, I didn't actually have a research grant. And so I can only resort to using very cheap technologies. And also at that time, never actually worked on cell-free plasma before. So I need a method which will allow me to very cheaply detect the fetal DNA in the plasma. So remember the time when I was a student in Oxford, the college food wasn't particularly delicious. So sometimes I'll go back to my room and cook instant noodles. So what you do is basically you boil some water and I put the noodles in, and then a few minutes later you have your dinner. So I thought, well, how about if I just take some plasma and just boil it for 5 minutes, and I take a few drops of that boiled soup to be tested. But surprisingly, even with this very crude preparation, I was able to detect the fetal DNA in maternal plasma. Now, as another example, I remember actually after we have shown that we can detect fetal Down syndrome from maternal plasma, then we asked, what is the limit of this technology? And then we thought, well, the limit has to be, can I detect the whole fetal genome sequence from the mother's plasma? So we were thinking about how to do this. Now, initially, I was thinking that maybe I can develop one algorithm which can solve that. So we've been thinking about that for about 3 years, but couldn't crack it. Eventually, one of those days, I actually went to see a Harry Potter movie with my wife. So I remember that movie was a 3D movie for the first few minutes. So we were sitting in a cinema, and I put on my 3D glasses, and I'm waiting for the movie to start. And then I remember the Harry Potter sign flying towards me, and then I can see the H of Harry towards me. And then suddenly when I saw the two stroke of the H, it's actually like 2 chromosomes. So suddenly I realized that maybe I need 2 algorithms, because every pair of chromosomes that a baby has got, it has 1 copy from the father and 1 copy from the mother. And then I need to have 2 separate algorithms, 2 separate formulas to do that. And so instantly, over the next few minutes, basically I've worked out how we can solve this problem. And then we solved that in a few months' time. So basically, inspiration from daily life is very important for me. The NIPT for chromosome disorders like Down syndrome has been introduced over 10 years ago. It's now globally used by millions of pregnant women every year. And some people ask me, well, what is the next step? Now, one next area which is useful to be explored is actually in the single gene disorders, diseases like beta thalassemia, cystic fibrosis, etc. Now, even though my group has actually shown that you can reliably use NIPT to detect those disorders, but because of the expense of those techniques, so still globally has not been widely adopted. And actually very recently, just this year, I was able to show that actually in the maternal blood plasma, there's a population of DNA which are very long DNA, because previously we and others have focused on the very short DNA molecules in plasma. And of course, if a DNA molecules are very short, the amount of genetic information it carries will be very little. But just this month, we were able to show that actually in maternal plasma, there's a population of very long DNA. And long DNA means that it carries many different genetic variations or even mutations that we can tell about the baby. And I believe actually using this technology, we're able to expand NIPT into single gene disorders globally. Now, another area which is worth exploring is that up to now, the NIPT is based on the look of genetic link. But recently, another field is called epigenetics, which is a modification of DNA molecules. Now, for example, you look at this room, the walls can be painted different colors. We can have different furnitures. And so the epigenetic modifications is that sort of modification. Now, for example, you look at me, in my body, there are trillions of cells. But my brain cell and my heart cell have the same DNA sequence, but yet they function differently. And one of the reasons is because the epigenetic modification of the different cell types in my body is different. And so we have shown that actually in the maternal plasma, we can also find those epigenetic information. And we believe this is important because some pregnancy-associated diseases like preeclampsia or even maternal gestational diabetes might actually somehow subtly alter or influence the epigenetic status of the baby. So we hope to be able to be pushing towards that direction. Now, another area which is worth exploring is the implication of cell-free DNA in blood to other disorders. Now, for example, you remember that just now I mentioned that I look into fetal DNA because I read a couple of papers in Nature Medicine about cell-free tumor DNA in blood. So now, with the advances in NIPT, maybe it's time to feed back into the cancer area. And indeed, actually, if we look at the last 20 years, we've been actually working in both of those areas in parallel. Now, for example, one of the cancers that I've been working on is a cancer called nasopharyngeal cancer, or NPC for short. It's a cancer of the head and neck region. And actually, we show that we can actually use this circulating DNA, now called cancer liquid biopsy, to detect this cancer very robustly. We can even screen for this cancer in apparently healthy individual. And if the individual is diagnosed with the cancer, I can use the cell-free DNA to tell what is the prognosis and what is the response to treatments, or whether the cancer has come back. And actually the screening part is particularly important because we actually shown in 2017, just a few years ago, that using a population of 20,000 citizens in Hong Kong, we showed that we can actually change the stage of detection from 76% currently without this screening method to 70% in the early stage disease. And we also show that the cancer which we discover from screening have a chance of dying of 10 times less than before. So we believe actually this screening is ultimately going to save lives. So now basically there's a lot of effort worldwide to actually extend this type of technology to screen for multiple types of cancer. And I've actually licensed some of this to a company which has actually launched a product recently. So I'm looking forward to seeing this sort of technology come to fruition so that we can have a weapon against this biggest of killer in many countries. Now, another area is in transplantation, because I remember actually after I discovered there is cell-free circulating male fetal DNA in the mother's plasma, if the baby is a boy, then I asked myself, can I see male sequences in the blood of a woman in other scenario? So I thought about a situation of transplantation. So let's say that I donated my liver to a female subject. Then I wonder, is it possible my liver might start to release my male chromosome in the blood of this lady? And the answer is yes. And actually we showed that back in 1998. And actually we can show that you can present that phenomenon in multiple types of transplant. So liver, kidney, bone marrow. And of course you will wonder, what is the advantage of that? The advantage is that basically cells release DNA in plasma when cell dies. And so there's one way to detect transplantation rejection. So now this discovery has been translated into a new non-invasive method for transplantation monitoring. I find research as being a very interesting endeavor because I look at this journey of discovery as a trip. Basically, it's a chance for me to travel to places and to see things which nobody else in human history has seen. So I think that is really a big privilege. So every time we encounter a problem, I actually look at that as being a way for us to get a glimpse into the unknown. And even though the journey is long, I would advise for the young people watching this video that actually it's not the answer which is the most important. It's actually the journey. It's like any trip. We don't just go there to the end of the trip. We go there to experience it, to go through the process. And actually, in many ways, I'm very jealous of the young people now who is going to science, because you have accessible to yourself technologies and knowledge that I could only dream of when I started this journey nearly 25 years ago. Now, for example, I remember when I first started, PCR was just coming in. But now, of course, PCR or other DNA amplification processes are routine. Now, for example, like in the recent COVID pandemic, we use PCR tests all the time. I also remember when I first started this journey, there was no human genome sequence. So it's almost like a sailor going on a trip across the Pacific, but without a map. But now you have that map, and actually you have many, many other maps. And also now, in many countries, the importance of technology innovation and investment are much better than 25 years ago. Now, for example, in Hong Kong, where I'm based in, so now the Hong Kong government is actually pouring a lot of resources and investments into R&D, which I could not imagine when I first came back here 25 years ago. So many people say that the 20th century is a century of physics. And actually, 21st century, I believe firmly, is to be the century of biology. And so if you're interested in this field, I'll say this is a golden time. Come, jump in and join us, and we explore the unknown and invent new things together. Thank you.